settle. Turns out that we are at your service every day of the week. We've got 3 TA officers. There's also a typo there. We've got this information on the website as well. So you've got TA office hours on Monday, Wednesday, Friday, and then I have my own office hours right after class, Tuesdays and Thursdays. Please take advantage of them. I know the TAs are dying to meet you. So, don't laugh. And it's in the big lab on NIDT. One minor thing, I think Nick does not have his office hours today. Tomorrow at the advertised time, it's changed to 4:30. Is that right? Mm-hmm. Yeah, it's changed to 4:30. Couple of other announcements. Quiz 0 is on Canvas. There was a question about where it is. It's on Canvas. It's due. It's open till I think September 3rd or something. Most of you have already done it. Please get it done. And there's also a survey on the website on Canvas again, and it's totally optional, but I just want to know who you are. I hope all registration issues have been fixed. Is there anyone who wants to be in the class and hasn't heard from me about this and hasn't been able to register? Okay, I'm assuming it's people who are coming late. So let's say that the registration is all fixed. And there was actually last week, there was an interesting, mainly last week, there was an interesting new textbook on machine learning that was released. It's available. Yes?
So just one quick question. So the homework 0 that you're talking about in class, is that quiz 0?
Yes, it's homework/quiz 0. Yes.
Okay.
Yes. Right, there was an interesting textbook that was released yesterday called Machine Learning. It's got a more theoretical focus. It deals with it's primarily a book on learning theory, but it's interesting. I've just added it to the class website. If you find any resources that you think is useful for learning, any prerequisites or anything, and you would like to share it with class, either put it on the discussion board or send me an email. I'll put it on the website as well. And yes, please use the discussion board for any conversation. There are some questions that come up, and if you think you have a question, I bet at least another half the class has the same question. So, and I see that there is some discussion going on already, but let's keep that going. Any questions about any of the logistics?
Will you post any suggested?
So every lecture comes with a bunch of suggested reading at the end on the lecture page. And so some of them, for example, just I point to a textbook. If you have the textbook, you can read it. I try to supplement any textbook resources with online stuff as well. Because there are a few machine learning textbooks that are free and online. But if you do want to buy the book, I'm not going to stop you. But yes, I try to post reading on lecture pages. So let me do a quick recap of where we are. In the last lecture, we saw the general setup for supervised learning. And we spoke about, at least I spoke about instances and labels. And the most important thing that we saw in the last lecture was the importance of hypothesis spaces. These are sets of functions that your learning algorithm searches over, and you try to restrict this set to be as small as possible. Of course, I did not answer questions 4 and 5 here because that would give away the rest of the class. But the key lesson from last week was about restricting the hypothesis space. And just to remind you, a hypothesis space is a set of functions that your learning algorithm considers. And if you consider all possible functions, then learning seems to be impossible because there are just too many of them. If you have, even if you are dealing with Boolean functions, if you have n variables, you have 2 power n functions with n variables. So the most reasonable thing to do is to select a hypothesis space that is small and yet is expressive enough. And some of you asked me at the end of the class, or maybe by email, I'm not sure, how do you know what to pick? I mean, yeah, this seems like a good idea, but there doesn't seem to be any magic. And yes, that's right, there is no magic here. You do some intelligent guessing. So, and if you're doing an intelligent guess, then you could be wrong. and you could probably pick a hypothesis space which does not contain even a single function that's correct, or it does not contain even a single function that fits the training data well or even well enough. So the game is to find a hypothesis space that's flexible enough, that's expressive enough to capture the target concept. So the primary issues in machine learning are, number one, how do you model your question as a learning problem? You care about a program, you don't really care about the math, but you still need to know how to phrase it so that the math can deal with it. The second question is that of representation. How do you represent your examples, and how do you represent your classifiers? And finally, there's the algorithmic question. What's a good learning algorithm? What does it mean to learn? How do you know it's going to generalize? And so on. And coming up, basically over the entire rest of the semester, we'll look at many different possible answers for all these questions. We'll look at different learning algorithms. We'll look at decision trees today, and an algorithm that can learn decision trees. We'll look at nearest neighbors at some point. We'll spend a lot of time on linear classifiers and the various algorithms that exist for linear classifiers. And we'll spend some time looking at how you can combine these different classifiers to make a committee that's better than any individual single classifier. But across all these cases, the primary issues that we'll consider are, okay, sure, you're going to find a hypothesis space, but we have to reason about what kinds of functions they represent. If you don't know what you're learning, it's not clear whether you're learning at all. The second thing is the trade-off between generalization and overfitting. And it's important to, at least when you're learning about a learning algorithm or a hypothesis space, what you should implicitly at least think about is what are the assumptions that are in place. If I'm using this particular algorithm, what am I implicitly assuming? And this is what will drive your choice for selecting a learning algorithm. And we'll try to, at least I'll try to list out these assumptions as we go along. And of course, the question of how to learn. Any questions about what we did last week or this general story of supervised learning? Yes?
What do you exactly mean by overfitting?
Good question. Overfitting is the property where your learning algorithm finds a classifier that does wonderfully on a training set, but doesn't generalize. The worst example of overfitting is you have a million examples, you put them all in a database, and you just look it up. When a new example comes in, if it's in the training set, you get the correct answer. If it's even slightly different, you don't. So that's the absolutely worst case of overfitting, but you could overfit without being that bad. In general, overfitting is when the training error is much better than generalization error or error on random examples that are not in the training set. And we'll see overfit. I'll keep talking about overfitting maybe even at the end of this lecture and through the semester. Other questions? Okay, let's jump right into today's lecture. It's about decision trees. So this is the first learning algorithm that you'll see, at least in this class. And I'll be answering at least two of the questions that I raised before in this context. One is what is the representation that the decision tree learns? What's the hypothesis space? And the answer is right in the title there, it's a decision tree. And the other question is what's a good learning algorithm? And there are many algorithms for this, and I'll mention just one of them. So the primary question we care about is how do we represent data? As I said before, you can always represent data in a big table, and we know how to do that. You can throw in, for example, instances in one column and labels in another column, and you have this thing. This is a data set that I had in the first lecture about names and labels. And as I said, this is not going to generalize. Another way of thinking about it is to featureize this data. Featureize every example. So you define a bunch of feature extractors that look up properties of the data, of the example, and you compute values of those properties. So for example, I've invented 4 features here. One of them is there a special character in the name? Yes or no? What's the second character of the first name? What's the last character of the last name? What's the gender of the person who owns this name? And so on. And for every question here, I can fill up an answer, and now I can pretend that my learning problem is not to map these examples to these labels directly, but instead go from a feature representation to the label. Okay? So let's say that we have all these feature vectors, but one thing to think about is how many rows can possibly exist out there for these 4 features, let's say. So the first column here, this one, is a boolean. It can be yes or no, it can take 2 values. This one can take, let's say, 26. This can take 26. And this is 2. And these are all the possible combinations that can exist. I'm making an assumption there are no special characters, and it's a very reasonable assumption. So what this means is the number of elements in this table, the number of possible elements in this large table, is the product of all these things. So there are effectively, even though there are practically an infinite possible number of names, when you commit to a feature representation, you're saying these are the only different possibilities that can exist in the universe. So in this case, about 2000. Might seem like a good thing, you reduce from infinity to 2000, but it's not all that great actually. So let's say you have 100 Boolean features. How many rows are possible if you have 100 features? 2 to the power 100. Try finding a database that can fit all of that. So it's really not a good idea. So what we need is a compact representation that can, at least, if not forget learning for now, compact representation that can represent all this data. Okay? So one answer to that, there are many answers to this, one answer to this is represent your data as a decision tree. Many of you might have seen decision trees at some point before in your life. How many people have seen decision trees? How many? Okay, I'm not going to ask how many of you have not seen because I bet some of you are shy. Decision tree is a hierarchical data structure. And you can think of it as representing data using a game of 20 questions. So, and as far as this class is concerned, this lecture is concerned, it's our hypothesis space. The space that we are going to search over is the search space of all decision trees, and that's the game that we're going to play. So, just to clarify, decision trees are trees, there are nodes and edges, and every interior node in the tree represents a question. A question about some attribute in the data. And you can take multiple parts out of that node. And the leaves of the tree represent a label. So, yes, well, I just noticed we have another announcement. Our third TA is in town, that's Abhinay. And he also likes to be bothered in office hours. So, anyway, the nodes represent questions about attributes, and the edges represent a value that every attribute can take as an answer to that question. And the leaves of the tree represent the labels. Let's look at an example. Let's try to classify shapes. Say I give you a data set with 3 labels, A, B, and C, and your job is to find a way of classifying these shapes without having seen any of them. I mean, without having to remember this data. So before we build a decision tree, I'm going to construct a decision tree for this. Before we build a decision tree, a question for you is, based on this data set, what's the label for a red triangle? Who said a random color?
What was that?
What did he say?
B.
B. Why?
Because it's red.
Because it's red. That's nice. And interestingly, because it's a triangle, also would work. So even without, so there's an example of generalization. Even without having seen a red triangle, you know, or at least you have a good guess as to what its label can be. So let's say I just give you this data set. What are some attributes that represents every shape? Color and shape. Those are good guesses because I don't know if you've already seen the slides, but those are good guesses. So you have color and shape. So let me build a decision tree. The root of the tree is going to ask, what is the color? So the input to this thing is a single shape, a single object. And first you ask, what's the color? And you have three possible options, blue, green and red. And if you open the blue edge, then you still don't have a single label, so you can ask now what's the shape. So what we have here is blue triangles are B and blue squares are A. And you agree that that's pretty much what the figure represents for everything that's blue. Right? Okay? When it's a red object, doesn't matter what the shape is, you don't even have to ask the next question. It's a B. Because everything that's red is B, according to this data. And for green, you can again ask the question of shape and you can classify it into two parts, square and circle, and follow the path. Yes?
For this one, we chose color arbitrarily first and then shapes.
Yes.
Is there one way to determine which one should be sorted first?
That's a good question for two reasons. The first reason is that's exactly an exercise I have at the end of this that you'll be doing. You can pick one or the other. As far as this example is concerned, it's not going to make a difference. The other reason it's a good question is because that is the central question that we have to answer in defining a learning algorithm that decides how to build the tree. Which attribute do you split on? And I'll show you one method, one algorithm that is a reasonable strategy. But yes?
Why isn't there a shape, a triangle with a green shape?
Right here.
Yeah.
Right there. Good question. The reason I didn't put it is hoping that somebody will ask the question.
So you don't have any information, I guess.
You don't have any information, so I don't have any, I have no way of doing this. But that gives me the next slide, which is how do you classify a red triangle? If according to this, a red triangle would just follow this path. You just follow the path from the root to a leaf, and the leaf, the label of the leaf is the label. The next question is, how do you classify a green triangle? So first you answer color, green, you go here, then you're stuck. So if I really want my thing to be general, you have to cover all possible attributes that this can take. And then that raises a question, what would the label be? And the answer to that is you have to make an intelligent guess. You have to generalize it to the most frequent label or something. So, questions about decision trees? Yes?
If you have to consider every possibility to be able to build a tree, then why is this any different than considering every possibility?
It is no different actually. We're going to talk about that right now. What's the expressivity of decision trees? What kinds of functions can decision trees represent?
Games.
Sorry?
Games.
Mathematically. Let's say we have Boolean functions. What subset of Boolean functions could a decision tree represent? You say that louder. Every Boolean function. The decision tree is giving us no more than just representing every Boolean function, except it's slightly more compact because you don't have to represent every possible value. For every example, you don't have to represent every label. Sometimes it can be more compact. But in the worst case, yes, you might end up representing everything. So that's exactly the next slide. you can represent every Boolean function using a decision tree. And one way to see that is, suppose that you had only two labels, true and false. Instead of ABC, suppose you had only two labels. Then every path from the root to a leaf is a conjunction. So you have, for example, color equals blue and shape equals triangle, then the label is B. Color equals blue and the shape is a square, then the label is, in this case, A. And you exhaustively enumerate everything and you can get pretty much any Boolean function. Because you can represent a CNF or a DNF using this. Questions about this? Okay, so what I have just told you is, here's a hypothesis class that is so expressive it can express anything, and so then there's a problem, because if we could express everything, then the search space is large, and we have to somehow figure out a way of learning. And that's the first point here. Optimally learning decision trees is intractable. Why? The easy answer there is the search space is too large. So we are not going to try to do that. But before getting into learning, I do want to talk about a few little minor details here. I'm assuming here that the outputs are discrete categories, A, B, and C. What if I want a decision tree that can predict a number? You can't have every possible number coming out of that node. So there is another object called a regression tree, which I'm not going to discuss, where at the end of every leaf you don't have a label but a function that produces a number. And the job is to find which function to pick. We won't be covering regression trees in class. And there are methods for handling noise in this data. Notice that that decision tree that I constructed perfectly fits the data, which means it's going to perfectly fit the noise. So there are ways of handling noise in this thing. We'll deal with that towards the end. And handling missing attributes. So if you have an example where all features are not available because maybe your sensor failed, maybe that function is too hard to compute, or maybe there's just noise in your feature extraction. And so there are ways of handling this kind of noise robustly as well. And we'll come to that at the end of this lecture, and maybe at the beginning of the next one. The other thing to worry about is, so it's good if you have discrete categories for every label, for every feature. So you can have color equals red, blue, or green. What if instead of that I have a feature like height or length? You're not going to exhaustively enumerate all possible real numbers coming out of the node. So how do we deal with them? Any ideas?
Create bins.
Someone who's not answered before. Okay?
Create bins.
Create bins. That's pretty much the answer. There are variants of that, but that's exactly what it is. So you discretize them. You have some thresholds that you define. You know these thresholds beforehand. It's part of design of the program, and you create bins. Just as an example, say you have two features, x and y. Both of them are real valued, and we are going to have to live with this because I have no idea how to get rid of it. So suppose you have two features, x and y, and I've given you training examples which seems to suggest that certain regions of this space are positive and certain regions are negative. And one way to discretize this is to define a feature, basically build a tree that looks like this. Is x less than 3? That's basically, this is 3 and this is 3 and this is 1. If x is less than 3, everything on... Okay, this doesn't get erased. If x is less than... Interesting. Oh well, sometimes programs have a mind of their own. as much as I try to convince you that's not true. So, right, so you discretize this by putting bins on the continuous features. So you have x is less than 3. If it's no, then you check whether y is less than 7. If it is yes, then it's basically y is greater than 7. It's basically this bin, so it's negative. And every box here corresponds to one path from the root to the leaf. And I've just invented these thresholds, and you can probably come up with some better ones. And how do you know what's a good threshold? You just think about it. You stare hard at the data.
It's kind of interesting how the threshold, I mean, you've got a condition on x at the root, and then you also have a condition on x on.
It's a different feature, right? It's a different condition to check on. There's nothing that prevents you from, because effectively those are two different functions. Less than 3 is different from, greater than 3 is less than,
different feature.
The one new concept I want to mention today, or now, is the idea of a decision boundary. Notice that a decision boundary is the surface in general, or the line that divides two classes. That divides, in this case, positive and negative examples. So, the interesting thing is, with a decision tree, the decision boundaries can be non-linear. And this is one of the few examples of non-linear decision boundaries that we'll be looking at in the class.
I'm just kind of thinking, with like a two-dimensional space, it's easier to draw out the boundaries and see where they are, but when you have multiple features, it kind of gets harder to eye that and say...
You can't.
Okay.
You can't. The only, in fact, if it comes to maybe with 3, you can build some sort of some visualization, but if it's a million, try plotting million dimensions on paper. So, at that point, the only tool that we have is algebra. We have to be able to prove, this is a proof by PowerPoint, which is not a valid mathematical technique, but in general, it's possible to prove that decision trees can produce nonlinear decision boundaries when your underlying space is real value. If it's not real valued, it's a different question. So, quick summary of what are decision trees. They are a hierarchical data structure. They can represent any Boolean function, and it's such a natural way to represent data that I'm not even sure who invented them. Many things you can put a name on who came up with this idea, but this probably seems like something you can come up with in a weekend. And I like to think of decision trees as playing a game of 20 questions. You start at the root and you keep asking questions, and at the end of the game you have an answer. The answer is the label. And so predicting with a decision tree is trivial. You just keep answering those questions. You just need to identify you just need to walk from the root of the tree to the leaf. And the one thing that I do want to mention is, given a data set, there doesn't have to be a unique decision tree that represents it. And I'm not going to answer why. I want you to think about, as an exercise, why it's possible that multiple decision trees can represent the same data set. But the question I do want to talk about is, how do we learn these things? Questions about decision trees, about what they represent and such things. Yes?
So, as you go along, if it encounters a new data structure that it has not done before?
What's a data structure? You mean a feature?
For example, let's go back to the circles, the squares, and the colors. Let's say all of a sudden it came up with a pentagon that was...
It crashes.
Okay.
So the alternative way of asking the same question is, can you be robust to, this can be seen as noise in the data. Can you be robust to noise? And there are multiple ways of doing that. Instead of answering pentagon, you try to take all possible paths and let the next levels decide, and you keep the uncertainty alive. That's one way. what I do want you to do is, as an exercise, I want you to go home and build a decision tree for the same data using shape as the root and not color, just to convince yourself that it's possible. And once you do that, you should be able to, you should try classifying examples of, these shapes that are not in the data to see if they give you the same label. And you should ask yourself, can you invent data sets where they disagree, where the two decision trees that you have will disagree with each other? The answer there is yes, but I want you to think about it yourself. Yes?
So, as and when you encounter new data, so you might have to restructure your decision trees right, and it would be difficult by looking at.
Yeah, so for now, at least for this lecture, so the question was, if you see new examples, you might have to go back and rebuild the entire decision tree, because that new example might force you to restructure the tree. How do we deal with that? At least for this lecture, let's pretend that we see all the examples. And this is the batch setting, where you have the entire training set, and you have to run your learning algorithm on it. We'll deal with cases where you can reconfigure the model as we go along, but not in the context of decision trees. So I can see you're all itching to get to how you learn. So let's talk about learning decision trees. But not quite. For that, I'm a total buff of history, so and I think everyone should learn history. So decision trees have been around forever. The oldest reference I could find was something in psychology, around the time that computers started getting used. Probably the first algorithm for learning decision trees is called Id3, and it was developed by Quinlan, and it has some roots going back to information theory. Maybe around the same time, probably a little later, there were also a bunch of algorithms called classification and regression trees, CART, that a bunch of statisticians from Berkeley and Stanford came up with. Over the next few decades, there were many improvements, tweaks to deal with noise, missing data, when you deal with weird kinds of features, dealing with continuous features, for example, such things. In the 90s, I think Quinlan updated this algorithm to get C4.5 and then C5 and so on. And these days, I think if you go to Veka, which is a software package that does machine learning, you probably can just get C5 out of the box. But of course, you won't be doing that because you might end up writing your own. And it might seem like decision trees are a bit unfashionable these days, especially with all the hype about neural networks and such things. But even as late as, say, mid to late 2000s, there were a few papers which showed that probably if you have maybe less than 300 features, a small number of features, 300 is a small number. If you have a small number of features, maybe the best black box learning algorithm that you can have is an ensemble of decision trees. Not a single one, but a huge group of them that act together. And this is called boosting or bagging, and it's a general purpose. It's considered to be a good general purpose learning algorithm because you learn nonlinear functions with some restrictions. So it's important to know this class of functions and learning algorithms for these things. I'm not going to cover this pretty much most of this because this is a huge body of literature. There's probably a good book, I think, that talks about decision trees if you care about it. What I will be talking about today is this Id3 algorithm, the oldest one, because it's so simple that the entire algorithm fits on one slide. And I'll also be, after talking about that, I'll talk about some of these sorted improvements that deal with noise, etc. So let's talk about the Id3 algorithm, and I'm going to introduce it using an example. Let's talk about playing tennis because the weather is good and all that. Say I want to train a classifier that should decide for me whether I should play tennis. This example, by the way, is from Tom Mitchell's textbook. Say I want an algorithm that decides whether I should play tennis. And the features that I'll look at of the day are mostly weather related. It's about whether it's sunny or overcast or rainy, what the temperature is, what the humidity is, and whether it's windy. And what I have to predict is should I play tennis or not, positive or negative? and I want to train a classifier that helps me make this prediction. And the first step in training a classifier is to go and collect some data. So let's say you played tennis for 14 days, or not played, you kept track of the weather for 14 days, and you decided, you recorded whether you played tennis that day or not. And let's say you have this table of examples, 14 examples. And I'm going to use this notation here, O, P, H, and W are the features, outlook, temperature, humidity, and wind. And each of them has multiple values. So, this is setting clear? So, the simplest algorithm is a batch algorithm. When I say batch, I mean you've collected all the data up front and you're going to do some processing on it. And the way it works is, remember that the decision tree is a recursive data structure. And the decision tree learning algorithm recursively builds it. So, just to give away the punchline before getting to the end, there is a tree that represents this data, and it's this tree. And what I'm going to do is walk you through an algorithm that builds this tree. And in the interest of confusing you, I'm going to present the entire algorithm up front before actually stepping through it. This algorithm is called Id3, and honestly I don't know what Id3 stands for. I'm sure it has an expansion. This is not all. I'm going to step through it. So, suppose, and the input to the algorithm is a data set and a target label. In this case, it is whether you're going to play tennis or not, and a collection of features. And what you do is, first, if every example in the training set has the same label, then the answer is easy. You don't need to build a tree, you just create a leaf with that label. If you're playing tennis every day, independent of whether it's raining or sunny or windy or whatever, then the tree is a trivial tree. It's just a leaf that says, yes, go play tennis. The more interesting case, that's the base case in the recursion. The more interesting case is if different rows in the table have different labels. So what you do is, we have to start constructing a tree. So we create a root node that we will eventually return. And what we do is pick an attribute. We have a collection of attributes. You pick an attribute that best classifies the data. And the crux of this algorithm is the definition of the word best here, and we'll talk about that later. So you pick one attribute that best classifies the data, and let's say for now we have a black box that defines best, and we have a feature A, which could be outlook or humidity or something. And then what you do is, you ask, what are the different possible values that this feature can take? And you create, for every value, you create a new tree branch. So, let's say you pick humidity, and it has, let's say humidity takes 3 values, you create 3 branches. Let's say high, low, and medium. Something like that. And now, you're sitting on, you need to now construct a subtree under each of these things. To do that, what you do is, you partition your training set into as many parts as there are values, and take the subset of examples which fits under this branch, or each branch. Let's call that SV. What do you do with the subset now? You recurse. That's it. So what you do is, now you have the subset is also a set of examples, and you have a list of attributes which is all attributes except for humidity, because you already used it up. So you have a list of attributes, you have a target label, you have a set of examples, you have to build a tree. What do? We have an algorithm that builds a tree, which is this guy. So that's but there's a slight wrinkle. What if there is not even one example for that attribute? Then you try to return the most common label under that subset. So if the subset is empty, then you return the most common label. If the subset is not empty, then you make a recursive call to the Id3 algorithm. Now, before asking why, if this is clear or not, one question to you guys. Why is it a good idea to do this? Why bother adding the most common label? This particular feature never happened in the training set. So why bother putting an edge in the tree?
It's kind of like the default condition.
That's the default condition, yes. Okay, so the follow-up question. Why the most common value?
Because that's the most, like, statistically that's something that happens very frequently. So for
Yes.
a condition that we don't know much
Yes.
about.
Exactly. The simple answer there is that lets you generalize better. It will probably give you, it's probably the setting that gives you fewest errors in the future. Questions about this algorithm?
What about if the set of attributes is empty? Like if we get down to like the base of the recursion or something, we just use the...
There are two options there. So let me throw the question back to the class. Let's say you are in this algorithm and this set of attributes is empty. You have some training data and there are no attributes left. You've used all of them up. What can happen? So let's say I make a call to this algorithm and there are no features anymore. I've come to the bottom of this thing, I've used up all the attributes and all inside that set. If all the examples have the same label, then you just create a leaf. If all the examples don't have a label or the same label, if there is still noise in the, or there is still some agreement among the examples that are in that subtree, what would you do?
Would that be an example of overfitting, or would
That could be an example of noise in the data,
Okay.
or it could be an
The list of features or examples, won't the most common value change as you get more examples?
Yes, absolutely, it will.
So
And as you get more examples, it will be more representative of what is the true most common value.
So should you wait until you go through all the examples to assign the most common?
No, but at any point inside this call, you have a list of examples, right? This data set S,
I see.
this set S here is a set. So you can compute the most common. Okay, let's walk through this algorithm. It's fairly simple and it's simple enough that I can actually step through the algorithm with an example. But the most important question here is this guy. The big black box is how do you pick what is the most common or the best attribute? Because if I define that, I have defined the whole algorithm. So this is probably the first time of many times that I will use the phrase Occam's razor in the class. And the idea is we want implicitly to bias the learning algorithms towards smaller hypotheses. Why? Because if you have a small hypothesis, the possibility of making a mistake with a very small tree or possibility of getting a terribly wrong small tree that perfectly fits the training set is very small. Let me rephrase that. Suppose you have two trees that fit the training set perfectly. One of them is much smaller than the other. Intuitively, you prefer the smaller one because it's a smaller explanation of the data. And this is this idea is called Occam's razor. And maybe in a few weeks we will see a mathematical formalization of Occam's razor. I just wanted to convey the intuition. Sadly, finding a minimum consistent decision tree is NP hard. We have no way of doing it in a reasonable time. So the algorithm I presented now, Id3, is a greedy algorithm. And this choice of best, we want to define it so that it biases our learning algorithm towards smaller trees. Maybe it won't find the absolute smallest, but we want to bias it towards smaller trees. So the question now is, how do we pick an attribute to split on? Is the question clear? Okay, I see two heads nodding, and I'm going to say that that's representative of the entire class. Unless there are people nodding the other way. Okay. So the goal is to pick a root attribute. And let's take an example to see how we might make this choice. Say I have a data set. Yes?
I have a question before that. Is it not that irrespective of which root we pick, we will end up having the same decision diagram or the same?
Irrespective of which root you pick, you will end up having the same, you might end up fitting the training set. You will end up fitting the training set because you're going to go all the way down to the tree unless there is noise in the data, or unless you come to these nodes that are not purely labeled. You've run out of attributes and you don't have any, your data set does not have a single label. In that case, you make a choice. You pick the most frequent one, and that's where these things will differ. Another reason why you might want to pick the attribute carefully is because if you get a smaller tree, so eventually we'll talk about pruning. You might have a depth limit up front. You might say that I only want to consider trees that are no more than say 3 deep or 5 deep. And if you're able to find a tree that is only 3 deep and perfectly explains the data, you like it. On the other hand, if you pick the wrong attribute, you might just get a very bad tree that's only so deep.
So it's more about optimizing the exact flow.
Yes, exactly. Let's come back to this example. Say I give you a data set with 200 examples. There are only two features, A and B. Both are binary. And when A is 0 and B is 0, the label is negative, and there are 50 such examples. It happens 50 times. When A is 0 and B is 1, it happens 50 times, the label is negative. When A is 1 and B is 0, the label is negative, but it never happens. In fact, it's not clear what the label is because it never happens. And when both are 1, the label is positive. So now the question is, say I want to build a decision tree that represents this data. What should be the first attribute to be split on, A or B?
A.
How many people say A? Most of you say A. And one of the reasons, I'm not sure why you said A, but one of the reasons for splitting on A is that you get the small tree. If you split on an A, you basically get the answer. When A is plus, you get, A is 1, you get a plus, A is 0, you get a minus. I could have split on a B, and you get a different tree that looks like this. You build a more complex tree. So, I don't know why you picked A, but one of the reasons to pick A is because complexity is not a good thing. But let's say now I change the game a bit. Say you get 3 more training examples with for this row here. So say you get something like this. Now the question is, what attribute would you split on? Yes.
I guess the big question is, could we label that as noise or not? Because
We have no idea. This is the data we have. Let's walk through this point. So let's say I pick B. You get a tree, and you should go back and convince yourself that I'm not lying to you, and this tree is actually, going to label the points correctly. If you split on A, you get a different tree that basically has the same number of nodes and edges. So these two trees are identical, structurally at least. Now I'll give you another, point out another piece of information that might help you make this choice. Let's look at the number of examples that exist at each leaf. So there are only 3 leaves in both cases, and in this case, there's 100, there's 50, and there's a 3. Whereas this particular path has only 3 examples. Now, let me ask you the question again. What's a better attribute to split on? Assuming, as you said, it might be noise, but we have no way of knowing. I hear A's and B's. It's, that's a good start. Those of you who say B, why would you say B?
There are more traits.
There's more common. It has more outputs, so it's more common.
What?
There's more attributes that you can find more solutions with B.
You're going to find the same number of solutions in both cases because both of these, for any example in the training set, is going to give the same label. So both these are consistent with the training data.
Then A is
So A because the left is,
Yes.
I would say A because you would get to the answer quickly for more data.
That's a good point.
I would argue that the tree on the left B is more robust because for each leaf it has more examples.
So you're saying that it's better to pick B because the leaves are more robust.
And then there are more examples to convince each part.
Well, there are the same. It's the same number of
But
examples overall.
For the right diagram, that path which has 3 examples, that's much convincing resolution.
Let me ask you another question. You're talking about this path, right?
Yeah.
Let's take that path. This path has A equals 1 and B equals 0. Right? And that's the same thing for a bunch of examples. Okay, this pen is occasionally working. That's the same thing. It doesn't matter when you have examples, those 3 examples end up coming here as well. So I'm going to argue that actually the advantage is for A because if, just as an intuition, if those 3 examples were noise, suppose those 3 examples were noise, then you want to take them and bucket them separately. You want to have fewer, you want to get to the answer as soon as possible. And if you pick A on top, for 100 out of almost 200 examples, for about half the examples, in one step you get to the answer. If you pick B, then for only a quarter of the examples, you get to the answer in one step. But this is just an intuition. There is a more formal way of quantifying this intuition. And that's really the way in which we'll pick a decision, pick the node. So just to remind you, the goal is to have the smallest or as small a decision tree as possible. And sometimes, even among decision trees that are of equal size, there may be a reason to prefer one over the others. Because as you go down the tree, you want to lose as much ambiguity as possible, as soon as possible. And the Id3 algorithm uses information theoretic strategy called information gain to design this thing. And I'm going to talk about information gain now. But a question for you guys. How many people have seen the word entropy before? Almost all of you. But how many people know the definition of entropy? Almost all of you. Okay, so let's take a detour. This is not a formal, rigorous definition of entropy or treatment of entropy. I'm just going to give you enough to help you understand what's going on. A set of examples, and I'm going to bias this towards what we need to know for defining information gain. Say you have a set of examples S, and say you have 2 labels, plus and minus, and suppose P plus is the probability or the fraction of examples that have a positive label, and P minus is the fraction of examples that have negative label. Then entropy is a way of measuring what is the amount of uncertainty in the data with respect to the labels. And it's defined as simply P plus or minus negative of P plus log P plus, negative minus P minus log minus. It's not fun to read out equations from a slide, so let's very quickly get to examples. But just to point out, this is not just for binary labels. If you have multiple classes, I can just define entropy as a big summation of pi log pi, the negation of that. And the intuitive way to think about entropy is it's a measure of uncertainty or disorder or impurity in the data. And to see why that works, suppose you have all examples belonging to one label, let's say plus. Then p plus is 1 and p minus is 0, right? And if you apply that this definition of entropy, you get the entropy of S is p plus, that's 1 or minus 1 log 0 minus 0 log 0. Yes. And by convention 0 log 0, we are going to assume it's 0, so both of these become 0, so the entropy is 0. And the way to think about it is, if the number of positive examples is, if p plus is 1, then that means every example is positive and there is no information there. If it's going to rain every day, you don't need to look at the weather report. You know it's going to rain. On the other hand, when both p plus and p minus are half, then this becomes half log half times 2 or negative of that, and throughout this discussion we'll assume that log is with respect to is log to the base 2, so half log 2 is 1, so entropy of the uniform distribution in this case is 1. So this is the side note about information theory. You can think of it as the number of bits needed to convey this information. If there is certainty, then 0 bits are required because you know the label. If there's uncertainty, you need more labels. The maximum uncertainty requires more number of bits, and the maximum uncertainty requires maximum number of bits. I can put this as a diagram. Let's say I have to get rid of this. I'm sorry?
The pen is highlighted, not the pen button.
Oh well. This is a quick review of what we did. Yes. So I can put this as a picture by saying, say I'm basically plotting histograms here. If you have very little uncertainty, most of the labels are positive, then the entropy is the blue bar here, which is low. If you have less uncertainty, or if you have more uncertainty, the entropy increases. If you have more uncertainty, the entropy increases, and the maximum entropy is when you have maximum uncertainty. And uniform distribution has the highest entropy, and this is true not just for binary, for two classes, but when you have more labels as well. This can be generalized to real numbers, but let's not worry about that. When you have multiple classes, say you have something like this, say you have 3 cases. Which of these has the lowest entropy? And as uncertainty increases, the entropy increases, and the highest uncertainty corresponds to maximum entropy. Okay? So, I hope this was a good refresher. I'm sure many of you have seen this before, but if you want to remember one thing, low entropy is high uncertainty. No, low entropy is low uncertainty and high entropy is high uncertainty. So let's go back to the question of picking the root attribute. What we wanted was to get a heuristic that lets us pick an attribute that gets rid of as much uncertainty as possible. And the information gain is a way of doing that. The way you do that is, say you have a data set S, and you want to pick the gain with respect to an attribute A. And the way you do that is, you first calculate the uncertainty in the entire data, and look at, for every possible label that the value A can take, you find what's the entropy of that subset of the data. And you take the average of that. This is basically the weighted average of the remaining entropy, and the difference of these two is the information gain. So you partition, so every attribute effectively partitions the data into different pieces, and you basically see how much this particular partitioning, how much entropy is, how much of the uncertainty is resolved by this particular partitioning, and the difference is what you care about. If the difference is high, then you know, or rather, if this particular value is high, then you like that attribute because it takes away most of the uncertainty. And I want you to, we'll be working through an example of how to use this, but what I want you to do is go back to that data set with A and B, and as an exercise, apply this strategy to those two data sets and find out which attribute is preferred. Okay? So, let's go back to the data set with tennis, and let's work through this problem of finding a root attribute. So we remember we had this data set before, and somehow this guy has reappeared. Anyway, we had this data set before, and the entropy of this data set is, there are 9 positive examples and 5 negatives, and I can just blindly apply the definition of entropy, and you get something like 0.94. No magic here, I'm just throwing in these numbers into the definition of entropy. And now what you do is you pick an attribute. Let's say you want to evaluate how good is this feature called outlook. So what you do is you first pick one value that this attribute takes. So when you say sunny, that gives us this row, this one, and these 5 rows. And out of those 5, 2 of them, actually 3 of them are negative, and 2 of them are positive. So this one and this one. So you have, and now I can calculate the entropy that's left behind for this particular partitioning of the data. So there are 2 positives and 3 negatives out of the 5 rows that have attribute value equals sunny, and I can calculate the entropy of this. I can do this for other possible values that the same attribute takes. Overcast gives you an entropy of 0, because every time this is overcast, turns out the label is positive. There's one more here which I'm not able to highlight. So the entropy is 0. And I can do the same thing for rainy, so you get the entropy of this, all 3 possible partitions. And now I want to calculate the expected entropy of this particular partitioning. So there are 5 examples from with outlook, with this number here, plus that number. So I'm calculating the expected entropy of the data that's left behind. Okay? And conveniently I have it on the slide, so the expected entropy, it turns out, is some number, doesn't matter what, and the information gain is defined as the entropy of the entire data set, which is the entropy of this set of labels, minus the expected entropy. So that gives us an information gain for this feature. And the reason I'm laboring through this process is because I want to point out that What we are doing here is just mechanical. And also I want to give you a heads up that this might show up in a homework very soon, where you might end up implementing this. Questions about this? Yes?
So does this mean you want to pick the attribute with the highest information gain?
Exactly. I'm defining best as the highest information gain. Or not me, Quinlan defined it for Id3. So we do this for one attribute. We did this for information gain of Outlook is whatever this number is, 0.24. I can now do the same thing for humidity, go through every value that humidity takes, and I'm not going to do this process again. I encourage you to, when you're home, to go through this slide and work it out yourself. And you can calculate the expected entropy and calculate the information gain. So it has another information gain. And you do this for every possible attribute. And the question of which feature do you split on, the answer is you want to find the information gain for every attribute and just pick the one that has the highest one. In this case, you split on Outlook. So that gives us the root node of our tree. So what we have is this sort of a proto tree, if you will, whose root is Outlook, and it can take 3 possible branches. And once you take a branch, you're left with only a subset of the data, because once you take this branch, only 5 examples still remain to be classified because you work, right? There are only 5 examples whose which come under this particular branch. And similarly, there are only 4 examples that come under this and only 5 that come under this. So you split the data set into 3 parts. And you can do this. Notice that we've already got a leaf node here, because once you take this path, the entropy was 0. This basically gives us a purely labeled data set. I'm just making up a name here, but this gives us a data set where every example has a plus label and no example has minus, so you can just say yes, or in this case it's actually plus. In the other 2 branches that we have, we need to still do more. Now, say we are sitting on a branch, this one, we need to recurse. This gives us the recursion step. We need to do the same process again and again. So let's take the case where Outlook is sunny. You're now left with a data set that's just a subset of the original data, where every value in the Outlook column is sunny. And now you still have 3 other attributes, and you have to basically apply the same process again.
Just applying this process with the entropy, does that minimize the size of your decision tree?
There is no provably minimum here, tree. It biases the algorithm towards smaller trees, because you're trying to explain as much data as possible at each step. But it's still greedy, because if you make the wrong decision at the top, you have to live with it after you go down. And I'm not going to labor through the process of building a tree for the rest of this process, but instead I'm just going to build the tree. So yeah, you can keep going on. And just to appease people who like seeing more program-like things rather than algorithms, here's a restatement of the same algorithm. So given a new data set, given a collection of examples that have labels, first you check whether that entire collection is uniquely defining a class. If every example in that collection has the same label, then you create it's not return S, it should be a leaf node with that label. Otherwise, first you find the most informative feature using information gain, and then you recurse. You create as many branches as that particular feature can take, and for every branch you have a smaller data set, and you call the same function again. You induce a decision tree for that smaller data set and just attach it to that branch. And at the end of this, you have a tree. In this case, you get the same tree that I promised you that we will. Question? Yes.
Can you remind me how you got the original entropy from the very beginning to start? How did you calculate the original entropy from which you start changing?
So what you do is first you calculate, okay, that's this step here. So before you get to the information gain, what you do is you calculate the entropy of the data set. And you subtract out the expected entropy of the split. Other questions? Okay, there are no questions. So now let's go back to this thing about hypothesis spaces. So we have an algorithm that can build a tree, and I said that this algorithm biases towards smaller trees without any theoretical guarantees that it will find the smallest one. So the question is, what is the hypothesis space here? And the hypothesis space is the set of all decision trees. So effectively, what functions are we representing? Some
Boolean functions.
the set of all Boolean functions. If you have Boolean features, otherwise the set of all discrete functions from the inputs to the output space. So yes, you want to search over all of those, and that's not tractable. That's NP hard, and Id3 is a greedy algorithm. There is no backtracking. Once you make a wrong decision at the top, you just live with it and keep going down. You will find a tree that's consistent. If your data is separable, Id3 will find a consistent tree. It may just be a lousy tree, but it will find one. And it's a batch algorithm, which means it uses all the data that's available to make a decision at each step. Questions about this? Yes?
What shall we do if we already use all attributes but we still can't decide?
You've used up all, that was the same question that came up before. If you use up all attributes and you still have no way of knowing how to label, because you are left with a data set that still is not labeled with a single label, then what you do is you can pick the most frequent label. I mean, that's one thing you can do. Or you can basically at that point decide that you're going to make it a coin toss that's biased by which label is more frequent, and such things. So there are a few different ways of dealing with it. The simplest thing is to just pick the most frequent label.
Is there any?
Is there any justification for this heuristic, or it's like a Show algorithm in some sense?
It's a what algorithm?
The Id3.
It's a heuristic. It's a greedy heuristic. And the justification is somewhat woolly in the sense of it biases towards small trees, and we like small trees because of Occam's razor.
So it's just like it's been observed to be always giving smaller trees than the others.
Not always. You can, if you want a particularly entertaining evening, what you should do is try to construct a data set where Id3 will not give you the small tree.
I was just going to kind of ask a similar point. Are there any results that say like this is guaranteed to give maybe within like?
Actually, I don't know. I have to look it up.
Okay, like within like twice.
Yeah, I don't know if there's actually an approximation guarantee here.
Okay.
I suspect not, but I'll look it up. Yes.
So when you're picking the root node, when you're calculating the information gain for that particular attribute, so if you find multiple attributes having the same...
you just pick one. You do something, but you be consistent with it. You can toss a coin there, or you come up with another criterion, which is not in the vanilla Id3, but you invent something. Yeah, and in fact, that happened in the data set that I had. There were two attributes. Oh no, it didn't actually. It did not. But you will, and the simplest thing you can do is just pick one, or pick an attribute that comes higher up in the alphabetical order, or something. Okay. That at least come up with a strategy that's reasonable and not biased. But unless you know something about the data, or you can come up with your own different tweak to Id3 that makes that choice. Okay, let me quickly summarize where we are. So we spoke about learning decision trees, or I spoke about learning decision trees, and I just want to remind you that decision trees are a hierarchical data structure that can represent pretty much any Boolean function. And searching over all possible decision trees to find one is not tractable. So we have to resort to some sort of heuristics. Id3 is probably the simplest such heuristic, which and probably the oldest one. And it's greedy in the sense of it tries to pick an attribute based on the maximum information gain, splits the data into multiple pieces, and tries to find more attributes and recursively just builds a tree. If the data, and the important thing to notice is, to realize is, you will get a tree at the end. There is no, unless if you make reasonable choices with these kinds of equal information gain and such things, you will get a tree at the end. And if the features are informative enough to separate the data, Id3 will find a tree that separates the data. Because there's nothing that says that, there's no, it's not a probabilistic classifier or something that keeps any uncertainty alive after learning is done. Of course, this is the simplest case, and there are multiple, things that there are multiple tweaks that we can have, and given that we have 3 minutes left, I don't think I can cover all of these, especially given that the numbering is also not right here. If the numbering is wrong, if the numbers are wrong, what do we have left? I'm going to talk about some variants of this algorithm that deal with handling noise or handling robustly handling missing features, or more interestingly, is information gain the only possible way of splitting data? Maybe there are other ways of defining what is an informative feature, and I'll briefly mention one more. And then I'll come back to this question of what do we do with features that are not Boolean when you have real valued features. But the bulk of the rest of the discussion with decision trees, I want to spend on overfitting. This will be our first exploration of the idea of overfitting, and we'll talk about how we can get around the problem of overfitting. Clearly, even if I'm able to finish the first 3 of these today, I don't think I can talk about overfitting. So let's get to that for the next lecture. Just for people who might have come in late, just an announcement: there's a quiz/homework 0 that's on Canvas. It's due, I think, Thursday.
On the 30th.
And good. And yes, I have office hours today right after class, so you're free to come and talk.